and it will talk about the Navier-Stokes equation and never-ending challenge. You have 45 minutes.
Thank you very much. Okay, first of all, I'd like to thank the organizers of this conference for giving me the opportunity to talk about my research area. And I also must tell that this is really the first step into Azerbaijan, and I appreciate very much the hospitality and the perfect organization. So thanks again to the organizer. Okay, I will give you an overview concerning the Navier-Stokes equation. There will be not so much mathematics, because the main purpose of this lecture is to introduce a little bit into the problem. So I will also start with some historical remarks. In 1904, on the International Mathematical Congress in Heidelberg, the German mathematician Ludwig Prandtl gave a main lecture about his new developed boundary layer theory. You can see him here standing in front of a so-called wind channel. That is to visualize different flow behavior by turning the wheel there with different speed and putting some obstacles in the channel. Around that time, nobody could imagine what a big progress fluid dynamics would make in the following years. Progress with respect to mathematics, with respect to experiments, and also with respect to numerics. The situation in the 19th century was indeed a disaster, as expressed by the following citation of a famous British Nobel Prize winner. Following Cyril Hinshelwood, there were more or less two groups dealing with fluid dynamics at that time. There was a hydraulic engineer who observed what could not be explained, and there was a mathematician who explained what could not be observed. By the way, I sometimes have the impression that people of both groups are still with us, but that's another thing. Horace Lamb was a very heavy mathematician. He wrote a very heavy book on hydrodynamics, and he had an excellent pupil, Sidney Goldstein. And Sidney said about his teacher that you can really read everything of the publications of his supervisor without coming to the real point. The difficulties that time were mainly due to the fact that the people studied the Euler equations describing motion of non-viscous fluid, so that the so-called hydrodynamical paradoxes appeared. Here the name paradox is a little bit misleading because these are not paradoxes in the mathematical sense, as the barber shaving everybody in town who does not shave himself. For example, D'Alembert's paradox, stating that there is no drag exerted on a fixed body in potential flow, no drag, no resistance. That's not a paradox, that's just a theorem which holds true if the assumptions are satisfied. That means if you have a really non-viscous fluid. But in reality, you always have small viscosities, so that this statement could not be true, as the experiments have showed that time. So these inconsistencies between theoretical considerations and practical experiments could be resolved later by people like Reynolds, Prandtl, Taylor, and many other mathematicians, physicists, and engineers. Finally, let me also mention the numerical mathematics, because the development of fast numerical algorithms, as well as the production of high-speed supercomputers, gave us a lot of insight into the structure of fluid dynamical problems. And these insights did not only influence the fluid dynamics. Many other branches of mathematics did profit. For example, the theory of partial differential equations, the potential theory, the functional analysis, the stability theory, the dynamical system theory, and even the numerical mathematics itself. They all got their benefits by the investigation of fluid flow problems. And in this connection, fruitful cooperations between mathematicians and engineers took place. And that all happens despite of the fact that the methods used in engineering sciences and in mathematics are of course quite different. Euclidean geometry is not enough to construct a bridge, but no mercy with a constructor who does not take into account the fundamental rules of geometry. Of course, it is quite hard for a mathematician to understand experimental details as it is for an engineer to understand the norm estimates a mathematician is used to control the flow. Here sometimes funny stories might happen. For example, if a mathematician tries to prove the existence of a flow to an engineer who has measured that flow since 20 years. This thing is of course based on a misunderstanding. Also, the mathematician has no doubt about the existence of that real flow, but his starting point is something different. It is a mathematical model of the flow. For example, an initial boundary value problem for nonlinear partial differential equations. And the existence of the solution of such a problem is not at all clear. So the insight that existence proofs are necessary is very old. It is as old as mathematics itself. For example, remember the history of the axiom of parallel lines. Starting 2,000 years ago, with Euclidean time, up to the 19th century, we try to prove the existence of parallel lines. So coming to the conclusion that it is not possible gave us new insights in the geometry. We could replace this axiom by other axioms, coming to non-Euclidean geometry, which later on were the basis of Einstein's relativity theory. But the merely existence of a solution is not enough for the practicability of a mathematical problem. And this friendly gentleman told us what we need. A mathematical problem is called well-posed if there exists a solution, if it is uniquely determined, and if it depends continuously on the data. Okay, the continuous dependence on the data, of course, expresses somehow the controllability of the physical process, and it is also highly desirable for numerical purposes because all the data in the computer have round-off errors, and during the simulation, of course, you want the deviation to keep controllably small. So the property to be well-posed of a mathematical problem is very important, and we will come back to it later in connection to the Navier-Stokes equation. So let me now introduce the most important person of my lecture. Navier was a French engineer who lived in Paris. He was a famous bridge constructor, and he wrote a very nice book about suspension bridges. This book, by the way, is still available in its original edition for several $1,000s in the internet. So if you like it, you can buy it. So, in 1822, based on a paper of Cauchy, Navier was the first person who formulated the equation of the motion of a viscous incompressible fluid. And this paper was quite hard to read. It was very long. And this might also be the reason that 12 years later there was another French engineer, Saint-Venant, who published a second paper improving and clarifying the results of Navier. Again, 11 years later, a third paper appeared. This paper does not contain anything new with respect to Saint-Venant's paper, but it got very famous and it was cited very often. So here they are, the three important papers concerning the equations of the motion of the viscous incompressible fluid formulated in the 19th century. So as the years passed by, people for some reason, forgot about the contribution of Saint-Venant. And that's the reason why I'm talking about the Navier-Stokes equation. I think that he must have known that, because he's looking very sad on that picture. Okay, life is hard and definitely not fair, and we do not know why he disappeared in this context, and some people have the idea that it could be because his name was too long. Okay. After having introduced the persons, let me come to the equations. I consider the Navier-Stokes equations always in a cylindrical domain 0t times g, where g is always a bounded domain in the three-dimensional space with a smooth boundary. Let me first explain the functions appearing in this system. V is a velocity field. It is a three-dimensional column vector consisting of the components v1, v2, and v3, and you have to imagine this system just as a column vector. Wherever you see v, so you have to imagine v1, v2, and v3. So p is a corresponding kinematic pressure function. That's a scalar function. Both functions, of course, depend on time and space. Then on the right-hand side, we have the so-called external force density. That's a three-dimensional column vector as well. And the kinematic viscosity, kinematic means we divide it by constant density. Also in the pressure, we divide by constant density. Is a positive number in front of the Laplacian you see there. And finally, we have v0. That's the only function depending only on the space variable. This is the initial velocity. So far, the functions appearing in that system. Let me come to the operators. Of course, dt, partial derivative with respect to time, and it is applied to each of the components v1, v2, and v3 in the first expression there. Then delta denotes the three-dimensional Laplacian. You just sum up overall second-order derivative with respect to coordinates x1, x2, and x3. Also, this operation is applied to the components. Then you have the gradient, which transforms the scalar function p into a vector function consisting of the elements d1p, d2p, and d3p. Finally, you have the so-called nonlinear term v times gradient v. This term is very, very interesting. It makes the treatment of these equations so extremely difficult. This term can be understood as follows. So first, you take the scalar product between v and the gradient, obtaining v1 d1 plus v2 d2 plus v3 d3. And then you apply this operation to each of the component v1, v2, v3 of v. That's the so-called nonlinear term. So let's come to the physics. The first three equations you see in the first line, these are three equations for each component. That's the balance of forces. And the fourth equation, divergence v equals 0, expresses the conservation of mass. In addition, on the boundary, we require the so-called no-slip condition. That means the fluid adheres to the boundary. This is the third line. And finally, we have the initial condition requiring that the velocity field should coincide to a given initial velocity, v0. So far, the physics. So these are, again, the Navier-Stokes equation. I consider the system in a fixed, given cylindrical domain. Given are the data f, nu, and v0. And the problem is to construct a velocity field v and some pressure function p. This system has been formulated in 1822, and up till now it has not been solved in this framework I just showed you. And the reason, all in all, you have a non-classical parabolic system. So what are the consequences? It depends on the viewpoint. Following Carlo Miranda, The Navier-Stokes equations mean an open door to hell. Following Kiyuya Masuda, the Navier-Stokes equations are like a jungle with rare fruits hanging in high trees. But these fruits are delicious. In any case, you know that around 2000, Clay Mathematical Institute has created 7 Millennium Prize problems, each of them $1 million, but what is much more important, a place in the Valhalla of mathematics. And the Navier-Stokes problem also belongs to one of these, is one of these problems, and the statement is the following. Also, the Navier-Stokes equations were written down in the 19th century. Our understanding of them remains minimal, and the challenge is to make substantial progress toward a mathematical theory which will unlock the secrets hidden in the Navier-Stokes equation. When I started as an assistant to study this problem, this was 81 and 35 years ago. Of course, in between there were some papers published. This is quite normal, where people stated to have solved that problem, and I want to go through shortly through this field. There was a paper appearing in the 80s, and my supervisor gave me that paper. I should find the mistake. This paper was given by Shmuel Kaniel from Israel. It was quite a long paper, 70 pages. On page 56 or so, there was a compactness error, so the paper was wrong. This was in the 80s. In the 90s, there was another paper by the Russian mathematician Bogovsky. It was very small, only 13 pages. This paper was also wrong. Then, in 2006, in meantime, we had the internet. You could find a homepage telling, this was shortly after the time where Gregory Perelman has solved Poincaré conjecture. So there were only 6 problems still remaining. And you could find this internet stating that, with a question mark, only 5 problems left. And the community was really shocked. But only for a short time, because Penny Smith withdrew her paper, A Mortal Smooth Solution of the 3 Space-Dimensional Navier-Stokes System, in 2006 due to a serious flaw. I don't know if you remember 2014 in springtime. 2014 in springtime, all the media reported about this paper. From Mukhtar Otelbayev from Astana University, he also claimed to have solved the problem, but also this paper was not correct. And 3 weeks ago, I was in Poland. I obtained a mail with that paper, Navier-Stokes equations, Millennium Prize problem. And if you see what's in the abstract, in this work we present final solving Millennium Prize problems formulated by Clay Mathematical Institute in Cambridge. I don't know about the correctness of this paper. I just want to mention that. It is also from Astana. The paper comes from 2 people from Astana. Sorry?
It's published.
Yeah, it is published this way. Okay, so far a little bit the situation concerning the Millennium Prize problem, and let me now come back. We leave the 19th century, we now come to the 20th century. And in the 20th century, of course, there are a lot of papers that appeared. And I personally think that these 4 papers are the most fundamental papers in the theory. Jean Leray, sur le mouvement d'un liquide visqueux emplissant l'espace. This guy, in 1934, introduced for the first time methods of functional analysis for the treatment of partial differential equations. We obtained from him the notion of a weak solution, and he showed that for the Navier-Stokes system, in the whole space, that means without boundary, in the whole space, there always exists a weak solution. It's a very, very fundamental result. But this did not hold for boundaries. It did not hold for domains with boundaries. So there was a second paper, Eberhard-Hopf, über die Anfangs-Randwertaufgabe für die hydrodynamischen Grundgleichungen, appeared in 51. He could extend the methods of Leray to the case of domains. So there was in addition a boundary, which is a particular difficulty. So the next very, very important paper done by Kiselev and Ladizhenskaya, they for the first time, I forgot to mention things. These so-called weak solutions have a very low degree of regularity, so it is not possible to prove uniqueness. The regularity is not enough to prove uniqueness. So people try to start to find unique solutions. And the first step in this direction was given by Kiselev and Ladizhenskaya. They proved that there exists a unique solution, but only locally in time. Only locally in time. What does that mean? That means you have not the given time interval 0t. You cannot solve it there. But you can give another time interval 0t star, which has a positive length, but it can be very small depending on the size of the data, such that in this very, very, very small time interval, you have a unique solution. These solutions are called strong solutions, and we will come back to that later. So the last paper by James Serrin. James Serrin was the first one who investigated additional conditions for weak solutions. So he was studying the problem. If we have a weak solution, we know that there is a weak solution, and we impose additional conditions. When will it be, which condition we have to take so that the solution is strong? So these are the four fundamental papers. Moreover, James Serrin also proved that the condition he gave always holds for the two-dimensional case. So in order to add this information, in case n equal 2, everything is fine and the problem is well posed. But in case n equals 3 up to now, we do not know if the problem is well posed or not. We do not know. Here they are, Jean Leray, Eberhard-Hopf, Olga Ladizhenskaya, and James Serrin, all are passed away. Okay, I mentioned weak solutions. The next slide is not so important. Okay. First of all, I want to comment on the second paper of Eberhard-Hopf a little bit. So, Eberhard-Hopf, in the second paper, was successful because he observed that the kinetic energy of a fluid is proportional to the LT norm of the velocity field. And so he was trying to find solutions of the Navier-Stokes system in L2. And he was very happy because Hermann Weil has just shown that the L2 for vector functions can be decomposed in two spaces. One space, the space H0, containing divergence-free vector fields, and the second space, G, containing the gradients. And because it is a direct sum, the scalar product of members of both spaces is 0. And now using the projection, the so-called Helmholtz projection, from the space L2 into the space H0, the gradient, as you see in the second line, with this projection was set to 0. It does not occur in the equation anymore. So the Navier-Stokes equation could be transformed into an evolution equation without the pressure. And using this representation, he was able to prove that there is at least one weak solution of the Navier-Stokes equation. So the theorem is as follows. Let t larger 0, let the data are given in certain spaces, then there is always at least one weak solution of the Navier-Stokes equation. Very, very important and fundamental result. There is at least one weak solution of the Navier-Stokes equation. Okay, now we go back to the fourth paper. Besides weak solutions, this is the definition, A weak solution has to satisfy three things. It has to be in the intersection of these two spaces. It has to satisfy an integral relation with test functions phi, and it has to satisfy an energy inequality. So these are functions with three properties. 1, 2, 3. These are weak solutions. And they always exist if the data are okay. So besides these weak solutions, we have something which is called strong solutions. And this was introduced by Sarin in the fourth paper. A weak solution is called a strong solution if there are numbers s and q, the so-called Sarin exponents, with s between 2 and infinity, q between 3 and infinity, satisfying 2 over s plus 3 over q equal to 1, such that the weak solution u is additionally in the space LS0TLQ. So strong solutions are weak solutions satisfying this additional condition u in LS0TLQ, where s and q have to satisfy these conditions. These are strong solutions. There are two reasons to consider strong solutions. This is the first reason. Strong solutions are unique. And this means the following. If you have two weak solutions with the same data, and if one of these two weak solutions satisfies Sarin's condition, then they coincide. So it's a uniqueness test. And this has been given by Masuda and Sarin. The second reason why we consider strong solutions is this one. Strong solutions are regular. And this means the following. Let us assume that the boundary is smooth, that the right-hand side is smooth, and that U is a strong solution. Then U and P are smooth. So strong solutions are very nice. So we have the following tableau. The whole set there contains the Lerey-Hopf class of weak solutions.
Can you look at the previous slide, I think?
Yeah. Thank you. So you see again here, you have the large set of weak solutions, and it contains a small set of strong solutions. Because per definition, a strong solution is a weak solution satisfying an additional integrability condition, the condition of Sarin. So on the right-hand side, we have the Lerey-Hopf class of weak solution. Existence is clear, uniqueness is not clear, and regularity is not clear. On the left-hand side, we have very nice uniqueness, very nice regularity, but we do not know if these solutions exist. So, and the problem, of course, is, the millennium problem is to extend somehow the dark blue set, to extend it somehow to the class of weak solutions. Or, in other way, to prove that weak solutions have additional regularity, to prove additional regularity for weak solutions which lie in the Sarin class. Then, of course, you can apply the uniqueness and the regularity statement. The only thing is, as I just told, the situation that strong solutions locally in time exist. The first result was given by Kiselev and Ladyshenskaya, and the second result was given by Prodi and Haywood. And they, Prodi and Haywood, they stated the following thing. As far as this function t maps to the square root of the L2 norm of the gradient of the velocity field, as far as this function is bounded, then the solution exists. So, and as we know also from Sarin's condition, that in the two-dimensional case, everything is fine, and in the three-dimensional case, we have problems. So we could try to illustrate what is the difference between n equal 2 and n equal 3. And this I want to do shortly in the following. So first of all, the energy equation. The energy equation leads to the expression below. The integral from 0 to t over the gradient of the velocity field L2 norm squared. This integral is always finite for all dimensions. It is always finite. That's the energy inequality. But that is not enough, because You know, if an integral exists over a function, this function must not be finite. We need the finiteness also of the function pointwise. And in order to get that, instead of multiplying here with a v, we have to multiply with second order derivatives. And as you can see here, the nonlinear term is orthogonal to v. But the nonlinear term, if we now apply, if we multiply with second order derivatives, is not orthogonal anymore. In this case, we obtain an estimate. And this estimate depends on the exponent here, and there you have the dimension. So for the case n equal 2, we obtain a 4, and for case n equals 3, we obtain 6. This term we can forget about. So we have dt of our function less or equal constant times function squared in case n equal 2, and dt of our function less or equal constant function to the power 3. This is the difference. And now you can shortly see how this works. We have this differential inequalities. The upper one for n equal 2 and the lower one for n equal 3. And if we now take the differential inequality and compare a solution of the differential inequality with a solution of the differential equation, and the solution of the differential equation lies above the solution of the differential inequality, because here we have the equation and here we have less or equal. So the solution of the differential inequality is below. And if we do that, then we can see that in the two-dimensional case we obtain a statement which does not fit with the assumptions that the integral is finite. A contradiction. We obtain in the two-dimensional case, we obtain a contradiction. Thank you very much. So we have the differential inequality, and we suppose that psi, the solution of the differential inequality, has a first singularity at t star. Then we take the differential equation. We can solve it. It's easy to solve. Calculus 1. You can solve it. It's looking like that. And if you integrate this phi, this solution, then the integral from 0 to t is the interval of existence, is infinite. And now you have the following situation. Psi is a solution of the integral equation. You know from the energy inequality that this square here, that this is finite. You have here the solution phi of the integral equation, of the differential equation. You can move it to the left. And you know that this one is not finite. This one is not finite. But this one is finite. So this is a contradiction. A first singularity t star in the two-dimensional case may not appear. It's not possible to appear. So, but in the three-dimensional situation, where we have the power 3 there, we can do the same, but the catastrophe is there. The integral from 0 to t is finite, so we cannot argue in the way to obtain a contradiction. So this is a short illustration of the difference between n equal 2 and n equal 3. So now, finally, I want to come to the last part of my lecture, very shortly, and now I will go a little bit deeper into mathematics. So, the question is the following. We know that strong solutions are nice, but we do not know when they do exist. And the question is the following. Let U be a weak solution with some given data. what additional regularity of the data is sufficient such that U is a strong solution at least locally. In other words, what additional regularity of the data implies that U is in LS0TLQ for some serine exponents S and Q? This is a reasonable question. And to answer that question, we need the Stokes operator. So PQ denotes the Helmholtz projection. AQ is the Stokes operator, with D of AQ given by the intersection of the Sobolev spaces there, range of AQ even LQ sigma, and e to the minus TAQ denotes the semigroup generated by AQ and LQ sigma. And with this semigroup approach, we can give the answer for that, sufficient regularity condition. Our first famous paper, Kassel-Ladizhenskaya. They said if the initial value is in the domain of A, which corresponds to H2 regularity in Sobolev spaces formulated, then you have a strong solution. So Brody-Hellwood, they could extend to A to the power 1 over 2. And then Fujita-Kato, 64, they could improve to only the fourth root of A. And as you can see, the domain of fourth root of A is contained in L3 sigma. So everybody tried to improve this to L3 sigma. But this took another 20 years in different steps until finally Giga in 86, more than 20 years later, could establish that U0 in L3 sigma is sufficient. And there are some more results. So this is a Lorentz space, L3 infinity sigma. It's even larger than L3 space. And finally, Ammann showed that if U0 is in a dual Bessel potential space, then this is also sufficient. So in the 50 years, starting from the famous result from 57 by Kiselev and Ladizhenskaya, the set of admissible initial values got larger and larger and larger, and the question is, what is the optimal condition? And this is, I want to give a final answer of this question. I formulate it once again. What is the weakest possible condition on the data, U0 and F, to get a local, in brackets, strong solution? The local is in brackets because if the data are small, then you don't need it. Because if the data are small, then you also have global existence. So, what is the weakest possible condition of the data U0 and F to get a local strong solution? Can we formulate conditions on the data U0 and F which are sufficient and necessary for U to be a local strong solution? And theorem 1 says the following. Let omega be a bounded domain with a sufficiently smooth boundary. Let S and Q be serine exponents, and let U0 and F be given in the correct spaces to get a weak solution. Then, the condition star you see below there, the integral from 0 to infinity over e to the minus tau0 in LQ to the power S. If this guy is finite, then this condition is sufficient and necessary for the existence of a unique solution U in LS0TLQ of the Navier-Stokes equation with data U0 and F in some interval 0t. So, as you can see there, the number t is not really clear where it comes from, and so I will also present the second theorem in a second. So the second statement is, let U be a weak solution of the Navier-Stokes equation with standard data, and let this condition not be satisfied. So this integral is infinite. Then for every t, Serine's condition U in LS0T LQ does not hold, and in every interval the system NS does not have a strong solution with data U0 and F and serine exponents. And a short remark, U in LS0TLQ if and only if V is in LS0TLQ, where V is e to the minus tau0. This is a solution of the homogeneous linear Stokes system. So you have the solution of the Navier-Stokes equation on the left-hand side is regular if and only if the solution of the linear problem of the homogeneous linear problem is contained in that space. And the second condition means if this is finite for all, if this is not finite for all Theron exponents S and Q, then for all Theron exponent S and Q and for all times the Navier-Stokes system has no strong solution for U in LS0TLQ. Finally, this is the last theorem. As I mentioned before, the time t, where does it come from? And the time t comes from the following statement. We have the same assumptions. So the main theorem is the following. There exists a constant epsilon, a positive constant epsilon, such that if these two guys are less or equal epsilon, and this depends, of course, on the number t, you can make this smaller and smaller by decreasing the t, the capital T. Then the Navier-Stokes equation have a unique strong solution, U in LS0TLQ, with data. So I will drop this. And finally come to a question which almost everybody has asked me. This is the question. And I will shortly tell you where it is. You have Germany here. It has been divided into two parts, left-hand side and right-hand side. The border was more or less going there. And there you see Kassel. It's in the center of Germany, just very near to that border on the western side. And if you come to Kassel, now we are also in the list of World Cultural Heritage. You get some impression here. This is a mountain park. If you stand up there, if you stand up there on the left-hand side tower and you look down in this direction, then you see this one here. You can see this one. And these are some more expressions. Thank you very much for your attention.
Any questions?
Professor, excuse me. Strong solution means classic solution?
Strong solution means insofar classic solution, because if the data are regular, then the solution is also regular. It means classic solution. Of course, it is firstly it is not formulated in the way that you have that all the terms appearing in the equation hold pointwise, but with a regularity theory you obtain that, and then it's a classical solution. Yes.
And I think in stationary case there is no problem. Stationary case. Yes,
in the stationary nonlinear case. In the stationary nonlinear case, there are also some very important problems, but uniqueness is somehow clear insofar as we can only have uniqueness under a restrictive condition on the size of the data. It does not seem to be possible to extend that, but there is, for example, there are other problems connecting with the stationary case which are important. There's a famous so-called Leray problem and so on. It's not everything clear on the steady nonlinear case.
Yes, we presented some sufficient conditions for stationary case in some paper.
Yes, it's interesting.
Yeah.
Yes.
I show you.
Thank you.
Any other questions? I just have quick. So there's theorems by you. The last two you showed.
Yeah, the last two theorems are.
How easy to check that condition? The one that you.
First of all, the theorem 2 I mentioned. This is the real work. The real work is theorem 2, and if you have theorem 2, then if you apply that, it is possible to find.
But the condition, the sufficient, necessary sufficient,
yes.
Is it easy to check given you use 0 and you have the condition with e power t?
It is easy insofar. It is insofar easy to check because you can just. Well, first of all, of course, you have to find the exact number of epsilon star, and the number epsilon star you have. It depends on the data, on the size of the domain, on everything. But you can more or less, for example, if you have a concrete domain, let's say a unit ball or whatever, or something with the size, then you can fix as a number, and then you can also fix the time. So we can control the existence time.
Any other questions? Oh, thank you.
Thank you very much.